So in this lecture, we will see the remaining portions of the chemical test. So there are many chemical tests. There are mainly 9 types of chemical pollutants which causes chemical pollution to water. So out of that, we have discussed these 4. The remaining 5 were there: alkalinity, acidity, nitrogen and its compounds, metals and other chemical substances, and total solids. So these are the other things which causes chemical pollution. So we will first move on to alkalinity. Alkalinity is the capacity of the substance contained in the water to take up hydronium ion to reach a defined pH value 4.3 to 40. Okay, so when pH value is greater than 7, it is a condition of alkalinity. Okay, so when its pH value is increased by taking up hydronium ion, then that type of water can be said to be alkaline. Okay, it is due to the presence of bicarbonate, carbonate, and hydroxide. And there are mainly 2 types of alkalinity. One is total, 2 components for alkalinity. One is total alkalinity, which is having a pH greater than 4, and another one is caustic alkalinity. It is a specific kind of alkalinity when the pH value is greater than 8.2, and it is measured in a volumetric basis. There are many indicators. We will use many indicators for titration. We will do the process of titration for determining the alkalinity. Many indicators are used there. Phenolphthalein is one indicator, methyl orange, bromocresol green methyl. So all these things are some indicators. Each of them have specific representation of alkalinity. When pH is greater than 8.2, phenolphthalein will give pink color, and when it is less than 8.2, it will give colorless. And methyl orange, when the pH is greater than 4.5, the presence of methyl orange will give an yellow orange color. When it is less than 4.5, it will give red. And bromocresol green methyl, when the pH is greater than 4.5, it will give greenish blue color, and when it is less than 4.5, it will give light pink color. And always the alkalinity is expressed in CaCO3, in terms of CaCO3 that we have already discussed about. Now, if the strength of the titrant solution is N by 15, that is normality is 50%, then the alkalinity expressed as total reading divided by volume of the sample in milliliter into 1000, normal representation. When the normality is 40, N by 40, now we can express the same equation in a different way. Alkalinity in milligram per liter of CaCO3 is equal to total reading divided by volume of sample into 1250. Okay, instead of 1000, we will give 1250. This 40 is taken into account. So that is the equation for finding alkalinity. And some other points you have to notice. The neutralization of hydroxide ion is complete at pH 8.2. So all the hydroxide ion will get neutralized at a pH of 8.2, and carbonate is only half complete at 8.2 and not fully complete until a pH of 4.5 is reached. So when we are neutralizing an alkaline solution, if the alkaline solution had a pH of 13, okay, we are neutralizing the alkaline solution by using some salt or some acids, and its pH is brought back to 8.2. Okay, now we can say that all the hydroxide ions in it get neutralized. Okay, but at the same time, carbonate ion is only half neutralized, and when we, even if we are reducing the pH up to 4.5, then also the carbonate ion is not fully neutralized. So that is a case of different alkaline ions present in the water. And when we are representing alkalinity on a pH scale, we can say like this: the total alkalinity is represented between a pH of 4.5 to 14. Bicarbonate alkalinity is 4.5 to 8.2. Carbonate alkalinity is 8.2 to 10 pH. Non-alkalinity, we can say that the water is not alkaline when its pH is 0 to 4.5. So this is the case. Now, how to determine this alkalinity? We have the result of titration here, which is in phenolphthalein reading, which is as a P is representing phenolphthalein reading. So we have the result of titration as phenolphthalein reading, where T is the total alkalinity. And hydroxide alkalinity is there, carbonate alkalinity is there, bicarbonate alkalinity is there. So when we have the result of titration, we can find all these alkalinities by using these equations. When the result of titration P is equal to 0, that is phenolphthalein reading is equal to 0, we can say that hydroxide alkalinity is 0, carbonate alkalinity is 0, but bicarbonate alkalinity is equal to total alkalinity. We can say like that. When P is less than 0.5 T, we can say that hydroxide alkalinity is again 0, carbonate alkalinity is 2 into this phenolphthalein reading, bicarbonate alkalinity is equal to T minus 2P. Like that we can say in all these types of alkalinities. We can calculate all the alkalinities by using this table or this equation. Now there are certain rules for finding alkalinity. So earlier day I have told you that carbonate and bicarbonate cannot exist together, but it can exist together. Okay, actually it is not true. Sometimes it may exist together. That is the thing. And it is assumed that bicarbonate and hydroxide alkalinities cannot come together in the same sample. Bicarbonate and hydroxide cannot exist together. Okay, that is one case. Alkalinity is only caused by three compounds: carbonate, bicarbonate and hydroxide. No other compounds can cause alkalinity. Hydroxide alone gives initial pH of about 10. So that much pH hydroxide can contribute. Carbonate will be present at pH greater than or equal to 8.2. When the pH of a water is greater than or equal to 8.2, we can say that the carbonate is present in the water. Hydroxide and carbonate together will give initial pH of 10. When these both are in water, the water will have a pH of 10. And carbonate and bicarbonate can exist together. Bicarbonate alone gives initial pH less than 8.2. So these are some of the rules for finding alkalinity. We can guess the amount or type of ion present in the water by means of its pH, on the basis of its pH. That is the thing. Now there are many advantages of finding the alkalinity of water. We can find the lime and soda ash required to remove the hardness. We can help to neutralize the acids produced during flocculation. It avoids the reactions between alkalies and other cations in water. It allows to take precaution against the increase in alkalinity. So all these are the advantages of alkalinity. And alkalinity less than 250 milligram per liter is desirable for domestic consumption and for RCC construction. So alkalinity should be less than 250 milligram per liter. Now we will move on to another important term. It is acidity. It is actually complementary to alkalinity. Acidity is the capacity of the substance contained in water to take up hydroxyl ion. Earlier, while explaining alkalinity, it was the capacity of the substance in water to take up hydronium ion. Acidity is the capacity of the water to take up hydroxide ion. Okay, hydroxyl ion, to reach a definite pH value of 0 to 8.2. Okay, actually 7 is the neutral pH, but if it is 0 to 8.2, then there is some presence of acidity is there. And acidity are of two types mainly: carbon dioxide acidity and mineral acidity. Carbon dioxide acidity is due to the presence of carbon dioxide, and it can be neutralized by titration to a pH of 8.2. And mineral acidity is due to the presence of hydrochloric acid, sulfuric acid, nitric acid and other strong organic acids. And the total acidity as calcium carbonate basis is equal to mineral acidity plus carbonate acidity. Okay. And there are many other advantages for determining this acidity in water. These are some of the advantages of determining acidity. It sometimes corrodes the pipe, so we can avoid the corrosion when we are determining the acidity. It decides the quantity of chemical dosages and line of treatment for industrial waste. It affects the biological treatment, so you can take precautions against this. It affects the aquatic life. We can take precautions against this. So all these are some of the significance of determining acidity of water. And it have to be noted that the acidity should be greater than 50 milligram per liter. If the acidity is greater than 50 milligram per liter, then it cannot be used for RCC construction. So this is an important point to be noted. Now we'll move on to the next chemical substance which cause pollution, metals and other chemical substances. So these are the different metals which causes chemical pollution in water. This maximum permissible concentration of these chemicals, which is given by the United States Public Health Services standards, is given here. So you can just read these. And another important chemical substance which cause chemical pollution in water is nitrogen and its compounds. Nitrogen can be present in four forms in water. One is free ammonia, albuminoid ammonia, nitrites and nitrates. So there are four forms of nitrogen occurring in water. The free ammonia, amount of free ammonia in water should not exceed 0.15 ppm in potable water. And it can be measured, the presence of free ammonia can be measured by boiling of the water. When we are boiling water, ammonia gas will be liberated. We can measure that gas and we can find the presence of free ammonia. And the second type of ammonia nitrogen compound present in water is albuminoid ammonia. The quantity of albuminoid ammonia should not exceed 0.3 ppm in potable water. And it can be measured by adding strong alkaline solution of potassium permanganate to water and boil it. By simply boiling, we can get the amount of free ammonia. But by adding potassium permanganate and boiling the water, then we can get the amount of albuminoid ammonia in water. And the third form of nitrogen present in water is nitrites. It should be nil in water. It should be nil in potable water. It is very harmful to human beings because it is not a fully oxidized form of nitrogen. So it is very harmful to organisms, should be nil in potable water. And the fourth form of nitrogen is nitrates. The highest desirable level of nitrates in potable water is 45 milligram per liter. And it is not much harmful to human beings or other aquatic organisms because this is a fully oxidized form of nitrogen. It is a common form. So it is not much having any health issues or problems. Now we will move on to the final type of pollutant which causes chemical pollution. They are total solids. The total solids are the residue in water left after evaporation and drying in oven at 103 degrees Celsius to 105 degrees Celsius, and it consists of dissolved and suspended matter. Solids, whatever solid present in water is known as total solids. Okay, we can find whatever things which are left behind after evaporation or drying of the water is known as total solids. It consists of, there are two types of total solids. One is dissolved and the other one is suspended. So first one is the dissolved solids. It consists of mainly the organic salts of carbonate, bicarbonate, chloride, sulfate, etc. Okay, so these are the things which causes dissolved chemical pollution due to the presence of dissolved solids. Now how can we measure that? We have to take the sample in a porcelain dish and we have to ignite it in a muffle furnace. We have to ignite it in a muffle furnace and then we have to cool it normally in air. After that we have to cool it in a desiccator and then we have to weigh it. Okay, so first we have to take the initial weight of the sample plus dish and then we have to weigh it after drying or flaming. So A and B are there. B is the initial weight of the dish and A is the final weight of the dish. V is the volume of the sample. When we are using this equation, we will get the total dissolved solids in milligram per liter. So this is very simple. We are just taking the sample, weighing it and igniting it in muffle furnace, cooling it and weighing again. So you will get the total dissolved solids by using this equation. And the dissolved solids greater than 3000 ppm may produce distress in livestock. It is very harmful and it may cause distress and may lead to scaling of boilers. And permissible total dissolved solids for drinking water as per BIS, Bureau of Indian Standards, is 500 milligram per liter and the tolerable limit is 1500 milligram per liter. So 500 milligram per liter and above is not good for health, but we can tolerate up to 1500 milligram per liter. That is the thing. Okay. Now the second type of total solids is suspended solid. Okay. It consists of inorganic matter like silt or organic matter like algae. Silt may be there, algae may be there, and it is aesthetically displeasing, causes diseases, provides absorption site for chemicals and biological agents. See, these are the ill effects caused by these suspended solids. How can we find the suspended solids in water? For that, what we have to do is we have to filter the water. Water is filtered through a fine filter, and what will happen? The dry matter will get retained on the filter. It is weighed, and after weighing, it will be transferred to oven, and it will kept for 1 hour at 105 degrees Celsius. Okay, so that is the thing we will do with this dry matter above the filter. And the filtered water, whatever things which is passed through the filter, that water is evaporated in a muffle furnace at 600 degrees Celsius for 15 to 20 minutes. Okay, so after that, at 600 degrees Celsius, the organic matter will be converted to carbon dioxide and water, and the inorganic matter will be converted to ash. So this also will be weighed. Now by using these two equations, we will get the total suspended solids and the suspended volatile solids. Okay, W2 is the weight of dry material retained on the filter. W1 is the initial weight. So weight of dry material retained on the filter minus initial weight of the sample divided by the total volume of sample will give the total suspended solids, and weight after evaporation minus initial weight divided by volume will give the suspended volatile solids. So these are the this is how we can find this amount of suspended solids in water. So with this we will complete this lecture. Thank you.